Our last topic for this chapter is standing waves and resonance. So let's get a picture of what we're talking about as far as a standing wave. If we look at this picture and we have a string that is connected to a fixed end, this is fixed, and on the other side we're producing some type of up and down action, and we'll say we're going at some frequency up and down. Then it produces a wave. Now it may be difficult to see, but there is one complete wave. If you take a look, this is the top part of the wave, and then remember, because this is fixed, it inverts and proceeds back. So if you were to take and fold this piece across, you would get the bottom part of the wave if it went all the way across past the fixed side. So we're just folding that back under. So this is 1 lambda. Now if we go twice the frequency, then we get 2 full waves in the same distance. So here's our first wave, and the second wave is inverted, coming back. So here we have 2 lambda. And if I vibrate it at 3 times the frequency, now I'm going to have 3 waves. I'm going to have 1 to this point, there's 1. Then I'm going to have, there's 2. And there's 3. Now these vibrations occur in integer sets, and the points where these waves tend to look at the 0 amplitude is, alright, these locations are called nodes, and an antinode is at maximum amplitude. So in this case, with the 3 times the frequency, I have 2 nodes and 3 antinodes. In the case of 2 times the frequency, I have 1 node and 2 antinodes. And then with the, I guess they're also counting this fixed end as a node, so there would be 3 nodes. This would be a node here. So 3 nodes, this would be a node. So there's 2 nodes, and here you'd have 1 node and 1 antinode. So these have to be in discrete frequencies. If I tried to do 2.5 times the frequency, then it would not be able to fit the waveforms into the length, and the amplitudes would come out very kind of wobbly if I tried to do 2.5. So only when you have some base frequency, 2 times the frequency, or 3 times the frequency, or 4 times the frequency, 5, you can keep going on down, and it's just going to add nodes and antinodes inside this length of the string. So if we have this length of the string defined by L, in this case we fixed both ends and we pluck the string, then the length is going to be 1/2 of the wavelength. So here, as we showed before, here's the one wavelength, and so the length is equal to 1/2 lambda. Now, since this is the bass frequency, we call this the first harmonic. And it's also, if you're dealing with music, you'll hear about them calling this the fundamental. I tend not to use the music terms. Most people don't understand that because after the fundamental you have what's called the first octave or first overtone, and the second overtone is after that. To me, it's kind of confusing because you're using first overtone when it looks like there's two. So I tend to work with the harmonics. So first harmonic is one antinode. Second harmonic, which is just 2 times the frequency, produces 2 antinodes. Third harmonic, which is 3 times the bass frequency, 3 times the first harmonic, gives you 3. So it's easier to understand in that way. And look at how the lengths will go. It's in terms of 1/2. So for the first harmonic, it's 1/2 lambda. For the second harmonic, it's just lambda, and that lambda 2 means that it's the second harmonic, and lambda 3 is just the third harmonic, and it's 3/2. So we can put this into a general form. If we have the length and I want some specific harmonic, is going to be equal to n over 2 times lambda n. Lambda n being your nth harmonic, n being your harmonic number, divided by 2 there. So n divided by 2 times lambda n. That gives the length in between the string, the length of the string in between these two fixed points. Now, to give you an example of how these waves are set up, let's look at this simulation that will start out with a wave on one side, and you'll see how once it gets to this fixed end, it'll invert, and then how you get constructive and destructive interference. So the wave starts, and so on the left side that would be like your hand moving up and down. The wave propagates down the string. It's going to get to the end here, and it's going to flip. Now the black line with the dots is what the string would be doing, and the red shows the incident wave, or the wave that you're starting with, and the blue is the reflected wave. So you notice that when the two waves are in phase with each other, or at the same point, when the red and blue cross each other at the same point, you get double the amplitude. But when the blue and red are inverted from each other, you get a 0 at that point. And so the amplitude is 0 when those are opposed to each other. So this is how a standing wave looks. Now you'll be doing a lab with standing waves, and there's some formulas that you're going to need to know, and that's going to be the subject of the next video.